Finxter. No, this is not how you write this thing. Maybe Finxter? No, also, this cannot be right. Something is missing here. Hey Finxter, what's up? It's Chris, founder of Finxter.com, and in today's video you're going to learn about the edit distance, or the Levenshtein algorithm, which is a very important algorithm for autocorrection. So often if you type in some words into your smartphone, for example, you type in Finxter with K and with this S, which is also not right, then your smartphone or your text processing program autocorrects the word you type in and proposes alternative words that correctly spell out the thing you want to write. So for example, in this case it would be Finxter, right? So this is a very important application for many practical scenarios. And how does it actually work? How does it know which words to propose, which words are similar enough so that it can propose those words, and which words actually to reject? And so one important algorithm in this area is Levenshtein algorithm. Bear with me for a moment. Levenshtein. So this was the creator of the algorithm, and it's an important term, I would say, important algorithm for computer scientists to understand, because it has some practical applications. So for example, the Levenshtein algorithm would compute the distance, how many edits you need. That's why it's also called edit distance, to go from one word to the other word, right? So for example, going from this word Finxter with a K and the S to this word has an edit distance of 1, right? Because you need to replace this K with an X, and then you obtain the original word, right? And then going from this word to the correct Finxter would have an edit distance of 1 again, because we need to remove the character S from this word. So going from this here to that would have an edit distance of 2, right? And this is actually how it can quickly generate high probability words in the dictionary that you may mean. So for example, if you type in the word Finxter with K and S, then it has already seen the word Finxter with an X, so the correct word, this one, and actually this is the word with the lowest edit distance to the word you typed into your word processing or program. And that's why it also is able to propose this one, because it takes, to generate high probability words that can be then later, in a later stage of the algorithm, it can be ordered, for example, by machine learning algorithms, or so, by the output of machine learning models that actually predict, that take this list of high probability words and actually apply a score to them, for example, how likely those are in a given context, and so on. So of course, today they will use machine learning algorithms to enrich this process, but a very quick and very efficient way is to actually have a first rough ordering of high probability words by means of the edit distance. Okay, so and this is the algorithm we will discuss in Python. So let's dive right into it. Maybe let's have some conceptual considerations first, because it is just much simpler if we have some. So how can I remove things here? So I actually want to. Okay, so now this way. Okay, so actually say we want to go from the word hi to the word hello. So we want to calculate the edit distance. How would we do this? Basically, we have 3 operations. First operation is to insert a character into the original word. The second one is to replace a character from the original word with another character. And the third one is to remove or delete a character. And this, with these 3 operations, we can basically transform any word into another word. And the minimum number of transformation or edits, each of those is called an edit. The minimum number of edits needed to transform one word, like hi, to the word hello, would be the edit distance. So if you want to, if you want to find the edit distance between those 2 words, we would basically, in one step, maybe remove the character I with the character E. so that our current word would be hi, okay? So now our edit distance would be 1 going from this word to that word. Okay, now what else can we do? We can insert new characters, like we insert an L, then we insert another character, another L, and then we go from here to here by inserting another character. Okay, so we have basically an edit distance of 1, 2, 3. So our edit distance going from hi to hello would be 3 edits. So 3 edits are needed to go from one word to the other word. And our method actually to do this thing, our general idea is the following. So first we have some concepts. First we will discuss the concept, and then I will show you the implementation. So if we have the word hi, now we basically create or generate the tree of all edits that are possible. So we can, for example, we can insert a character into each position, right? We can delete each character from this word, or maybe let's just consider the first character. Yeah, I think it makes sense to only consider the first character, and then we can remove the first character. So, for example, if we remove the first character, we obtain the word I. If we delete what was it? So we have replace. Oh, sorry, this was so we have this one is delete. So this would lead to I. Now we can replace the first character with another character, say G. Of course, we can also replace it with other characters. So we have like a tree of different possible replacement. We can also insert some values like an E between H and I. So we can do a number of replacement insertions here. And now for each of those words, we also can perform a number of operations like inserting a character, removing a character, or replacing a character. And for each of them, for each leaf in the tree, we basically can perform one of those operations, and then again for each of those we can do the same, and we can do the same. And basically we want to find a leaf, like our ultimate goal would be the word hello. Okay, and so we're going from hi, we go from the word hi to the word hello by actually following these steps from here to here to here and to here. Okay, it doesn't make sense a lot in this tree, like the concrete ordering of the operations, but I mean, you get the concept, right? We have an original word, and we have some nodes in a tree, and we basically search the path going from the root of the tree to the leaf of the tree, and the root is our original word, the leaf of the tree is our target word. And of course there are many different ways of reaching the same word. Maybe we can also reach it quicker using another branch in this tree, right? Maybe. So for example, we could first remove all characters of a word and then insert all characters, and don't replace any characters. And in this case, it would be like this could have an edit distance of say 10. But then there is another way of just replacing two characters, and this could have an edit distance of 2, for example, yeah, in some instances, in some combinations of words. So actually, there are many different leaves that actually have this that look the same, but the path of reaching this leaf is different, and therefore, like, we want to find the shortest path in this tree. And so how do we do this in the code? So now we have done some conceptual work here, and we can maybe dive right into the code. So our general idea would be, so let's open the code, and so our general idea would be to sorry, I have to fix something. So we create a function called Levenshtein, and we have two words that we put in, like word A and word B, and those are the inputs for our transformation. So for example, it could be later, like if we maybe let's make this just so this is the general so how the function actually looks like from the outside. And now we would call, for example, Levenshtein cat to cello and our target would be, say we want to, like, what is our goal? Actually, we want to find the edit distance. We want to find the how to replace basically how many edits are necessary to go from cat to cello. So for example, we can replace the A with an H, we can replace the T with an E, and then we insert 3 characters. So we have like 5 replacement or so. So the result probably should be 5. Maybe I missed something, but this should be the general idea. Okay. So up till now, just to summarize quickly, the Levenshtein distance is a metric measuring the difference between 2 strings. And if 2 strings are similar, the distance should be small, right? If they are the same, like the edit distance is 0, because we need 0 edits to go from one to the other. And if they are very different, the 2 strings, then the distance should be large. But what does it mean for 2 strings to be similar or different? And this is basically the metric is defined as the number of edits, and an edit can be an insertion of a character at a given position, a removal of a character, or a replacement of a character with another character. So this is our goal basically, yeah. And okay, so now let's dive into our algorithm. First, we check if one of the string is empty, right? If not A, we return the length of B. And if not B, we return the length of A. So why is that? It's very simple. So for example, say our string A is has 3 characters, and our string B is empty. Now basically, if not B, evaluates to true. Because B is empty, this is called implicit truthiness of Python object. So each Python object has an associated Boolean value, and if the Python object is empty, then the Boolean value of this Python object is considered false. So we check if it is considered empty, if our string is empty. So this is true. Like this would be evaluated to true only if the string is empty, if B is empty. So if B is empty, we would go into this branch. We return the length of A. And the length of A, so for example, say A has 3 characters, and of course we need to insert 3 characters to go from, no, actually we have to remove 3 characters to go from A to B, right? So say A has 3 characters, B is empty, the empty string, so we need to remove all 3 characters to go from A to B. This is like a trivial solution, or also called the recursion-based case, because we use recursion to solve this problem, as you will see in a moment. And similarly, if A is empty, we basically need a number of insertions going from the empty string to the number of characters in our string B. So say if the string B has 3 characters and we start with an empty string, we have to insert 3 characters to go there. So basically in those 2 cases, the solution is trivial. Okay, so now and in these cases we are done. So for example, now we could already execute this. Maybe let's get back and copy this. And in this case, our first string is empty. In this case, the result should be 5 as well, because we have like 6 actually, because we have 6 characters in the string B. So let's check if this is the case. 6, this is the case, okay? And now in the other case, the return value is none. Why? Because in this case, we don't return anything, yeah? So neither the string A is empty, nor the string B is empty, so we don't go into any branch, we don't return anything, so we still need to do something. We are not ready yet. Okay, so now we need to simplify the problem. This is the beauty of the Levenshtein algorithm, that we can repeatedly simplify the problem. So for example, if we had already found a solution of the simpler problem, like going from add to hello, if we would already have found the minimum number of edits needed to going from add to hello, then we simply need to do like one more check. So we need to check going from C to C, right? In this case, it would be 0. So the minimum edit distance would be 0 plus the number of edits needed going from add to hello. Okay, so we can simplify the problem using the simpler problem to construct the more complicated case with more characters. And so our idea to simplify the problem uses 3 ways, and we will discuss these 3 ways in a moment. So first of all, we ignore the leading characters of both strings A and B and calculate the added distance from those substrings. Okay, so this is what I already told you. We ignore the first characters, we're going from add to hello, and we calculate the added distance going from those in a recursive manner. And how do we get those? Yeah, we use slicing to go from there. So so our solution would be the minimum among 3 cases. So we have like here maybe let's just write case 1, case 2, and case 3. And so this is like it returns the minimum added distance among those 3 cases. And what are the 3 cases? Now we have already, like I've already told you, the first case, kind of. The first case is the Levenshtein distance going from, so first I will write it and then I will read it to you or explain it to you, plus checking if the first characters are different. And here I did a mistake. Okay, so this is our first case. We basically return, so the Levenshtein function calls itself, but on a simpler problem. And in this case, as I already told you, it uses slicing notation, going from the index 1, which is the second character, to, if you have troubles understanding slicing, I will give links in the description below to another video where I introduce slicing. Basically, before the column we have the start index, after the column we have the stop index, but we don't stop anything, and we try to like get a subsequence, get a substring from just ignoring the first characters. Okay, and this is like this slicing notation means we ignore the first character but use the remaining whole string. So for example, for this input string, if this would be A, then we would simply ignore the first character and just use add, right? And for the input cello, so if this is for example B, we would simply use B. We slice from the character with index 1, which is this one, all the way to the right, so we have hello. So basically what this means is we call the function on itself on a simpler problem by just removing the first 2 characters of our strings A and B. So this is a simpler problem, right? And you can already see by simplifying the problem repeatedly, the input of the Levenshtein function will become smaller and smaller. And at one point, it will be empty. It will be like either A or B will be the empty string, and in this case, we return the trivial solution. Okay, so we repeatedly reduce the complexity of our problem, simplify it by putting smaller and smaller substrings into the Levenshtein function, and at any point in time we basically get the trivial solution. If either one A or B is empty, we get the trivial solution. And but in this case we are not ready, because the Levenshtein distance of A and B is not the same as the Levenshtein distance of both strings, of both substrings starting with the second character. Why? Because, I mean, in this case it is, right? Because going from add to hello, say the Levenshtein distance is x. Now in this case we don't need to do anything else because C is already the same as C, right? So we don't need to replace C with C or so to obtain the Levenshtein distance x plus 1. So basically in this case our Levenshtein distance would be x. Because like the solution for the more complex problem is the same as the solution for the simpler problem, because the first 2 characters of both words are the same, so we don't need to replace them. But it could be it could be that the first character, the first input would be in D, and for the first word, and for the second word it would be a C. So in this case we would have to replace the D with a C to obtain the first character, to obtain the same first character. Okay, and so basically we need to check, are the first characters of both strings equal or not? So in this case we check whether they are not equal. If they are not equal, the return value is true, Boolean true, which is represented by an integer 1. In this case, we add 1 to the Levenshtein distance. Remember, this one, the result of this operation is an integer value. So we get an integer value of the Levenshtein distance, of the difference between the two strings, ignoring the first characters, and then we add together whether both characters are the same or not. If they are not the same, we basically add 0. So because if they are the same, the result of this comparison is false, which is represented by an integer 0. So we add 0 to it. So we add 0 to our Levenshtein distance, and if they are the same, we add 0. So we have the Levenshtein distance of the more complicated problem is the same as the Levenshtein distance of the easier problem. But if they are different, we need to replace them and add 1 to the Levenshtein distance. So this is our first case, and this first case is just like changing the first character. Okay, so this is our first case. So we change the first character or not, and if we change it, then of course the Levenshtein distance of this more complicated problem is 1 larger than the Levenshtein distance of the simpler problem, and otherwise not. Yeah. So, but this is not the only case. We could also have a case like this is only the basically this is only the replace operation, replace on first character. But we could also do other things with the first character. So, for example, we could also remove the first character. Remove first character. So this is also a thing that we can do with our current, like with the first character, right? Because we have the 3 edits. We have replacement, removal, and insertion. And so now we basically take the first character, we take all the characters but the first, except the first, from the first string and all the second string as is, and add 1 to this. So I will explain this in a moment. So this is our second case. Why is that? Because like conceptually we can remove the first character from A to obtain the second Levenshtein distance. Okay, so this is also like, this is one branch that we can execute. So basically, again, we call the function itself, the Levenshtein distance itself, on an easier problem. So now the string A is the easier problem. So basically by removing the first character from A, we simplify the problem, and we go one step. We may go one step further to our solution of reaching B. But in this case, if we have done this removal operation, basically, we in any case have added an added distance of 1 to the more complicated. So to the more complicated solution. So if we use this solution, we basically have to add 1 to our Levenshtein distance. So we take the Levenshtein distance of the easier problem, the problem where we simply ignore the first character of A. So say in this case we have found the minimum added distance from add to cello. So we take all the characters from the first word but except the first, and we take all the characters of the second word. So now we have found the minimum added distance from add to cello. Now what do we need to do? We need to remove C, right? So by removing C, we basically have reached the state where the first word is add and the second word is cello. So now we can basically reduce this problem to the simpler problem, which we have already figured out here. But then again, we have to add 1 because we have done one removal operation. So therefore, this is the second case. And okay, then what is the third case? The third case is conceptually to insert first character. So again, if we have found the Levenshtein distance from cat to hello, so we have the whole first word cat, and we have found the Levenshtein distance of hello already. Now what we need to do, going from here to here, is to basically simply insert a character, right? To the first character, character C, to get the Levenshtein distance from cat to cello. Because we have already found the way to go from cat to hello. So going from cat to cello is simple by just inserting one character C in the beginning of the string. So in this case, we need to do the following. We again call Levenshtein on A, and using all characters except the first one of our string b, as I have shown just previously, and we again add 1 because we have performed one insertion operation in the process. So basically now we have replaced our complex problem by 3 easier problems. So we have considered all 3 problems. So we have replaced the first character from both words. So from the one word, replaced the first character with the first character of the second word. We have removed the first character of the first word, and we have removed the first character of the second word. And those are all 3 cases we can do with the first character of our problem. And then we have simply reduced the problem to the remaining characters. And we don't care about this because this is done recursively by our function, right? Now our function, next time we call the Levenshtein functions, for example, on this subproblem. This subproblem is like the inputs to this subproblem are smaller than the inputs to the bigger problem. So as they are guaranteed to be smaller because the strings are smaller, like this is the original string of course, but the string B is smaller. So either the string A gets smaller in this case, or the string B gets smaller in this case, or both inputs get smaller in this case. The inputs get smaller and smaller and smaller in each function execution. And therefore, finally, so sooner or later, we will for sure reach one of the base cases, the recursion base cases. And in these cases, so as we reach them, sooner or later, we get the trivial solution. And we use the trivial solution to successively construct the more complicated solution by this plus ones, or plus ones or plus zeros in the first cases. And we take the minimum in each step. In each recursion step, we take the minimum to bubble the minimum up because we are searching the minimum added distance, right? So if you had trouble understanding this, then go ahead, go over the video once more. I guarantee you will understand much more regarding the added distance. But I mean, that's it. That's a code. It's pretty simple. You see, it's just a few lines of code. But the algorithm is very elegant, very efficient, okay, maybe not so efficient because it's like a recursive version, but I think it's an elegant algorithm showing the power of recursion. So let's get rid of those comments and run the code. And now you see the result is 6 and 5. And for example, if you go from like chess to cello, now we only need to replace those 2 with else and add an O, so our result should be 3. So let's check if this is the case. 3, okay. No, so now this is a very simple algorithm that gives you the similarity between 2 words by means of the added distance. Okay, thanks for watching this video, and keep at it, keep watching videos of Finxter, keep improving your skills over time, because knowledge compounds, as you know. So if you master those type of simple algorithms, it becomes much more easy to master more complicated algorithms and like moving up the food chain. Thanks for watching the video, and see you in the next video. Bye.